Today we're going to talk about Module 5, Lesson 4, Investigating Sound, Simulating Sound Travel. In this lesson, they're looking at what it would look like if we could see the actual atoms in the air as sound moved from a vibrating source to your ear. So they start off with a question: if you could watch the motion of a single particle in the medium, what would you expect to see it doing as sound travels across the medium? So they have a simulator to help you visualize that, and there's a link that you can go to. When you end up going to it, it'll bring you here. You need to come down to the Run NetLogo web and the Click to Run Model. Okay. When it comes up, there's different things that you can adjust. You can adjust the speed of the model. You can adjust the amplitude, and we will do that, the number of vibrations, and the frequency. So we're going to set that on fast, and we want to go to Setup, and that'll show us our model. The first thing that they want you to do is they want you to run the model, and they want you to watch the motion of one molecule. And the way you do that is you hit Go, and you choose any one of the circles. And when you select it, it'll end up showing up red, and you can watch the motion of that molecule, how it moves as a wave is being formed. Or what I could do is I could select another one out here, and I can watch it in a different area, or I can watch it out here. So they want you to describe what you see that molecule doing, and then what's going to end up happening as we change this. So I'm going to go to pause, and when I hit setup again, it resets it back to 0. So I'm going to do it with my amplitude as low as it can go, and do go and select one, and we can watch what happens. Okay, there's not a whole lot of movement in there. So let's pause it. Let's reset it. And then we'll turn it all the way up. We'll hit go and we'll select a Okay, so you notice that the clumps that it's making, these dense areas, are a little bit bigger when I have my amplitude turned up. I'm also going to look at the vibration frequency, and we're going to try that set at low. Everything really slows down. Go to setup and we'll turn it all the way up again. Okay, so that makes the orange vibrate a little bit faster. So what I want you to do is go through this and adjust some different things and try to find patterns on the way these molecules are moving compared to these molecules, and what amplitude change does and what frequency change does. The next thing they want to do is they want you to describe the images from the simulation. So these would be still shots of what you just saw. And they want to know what the darker bands are called. So this is a compressional or a longitudinal wave. In a compressional wave, you have areas of matter that are all bunched up. So as this moves forward, it pushes these molecules together, and it's going to make a denser area, and that's called a compression. When this pulls back away, the matter goes with it, and it makes these areas that are not very dense, where the molecules are spread out over a larger area, and those are refractions. So in a sound wave, you have compressions, right? The darker areas are your compressions, and the spread out, the less dense areas, are your refractions. And you could do the same thing where you can measure the amplitude by how big the compression is, how compressed it is, and you can measure wavelength, the distance from one compression to the next, or one refraction to the next refraction. And then they want to know, why did that happen? So when you want to know that this, right, this is the vibrating source, whatever it might be, and that surface pushes these molecules together. As they push them together, it makes a compression. And the reason they spread back out for number 5 is as it pulls away, it creates a vacuum, right? There's no matter there. And since this is a gas, it's air, it goes back in and it fills up that empty area. So that's why it spreads back out. And the next thing they talk about is they try to explain density using these boxes. So if you notice, each one of these boxes has the exact same number of dots. There's 9 dots in each one of these, and the dots stay the same size. But what they do is they reduce the size of the container, because when you talk about density, you're trying to relate the mass, the amount of matter, in a unit volume. So they take the volume and they reduce it, and this is the least dense, till all the way down here is the most dense, because they take the volume and they reduce it, same matter, reduce it, same amount of matter, reduce it, same amount of matter. So this one has all the particles very close together. So that would be like the compression. And up here, they're very spread out. It's less dense, and that would be the refraction. So the thing that you need to learn from this lesson is you need to know that if I watch an individual particle, it does move back and forth. It doesn't stay stationary. But what doesn't happen is it doesn't move along with the wave. This one particle isn't transported from one area and comes all the way down here and ends up right by your ear. All this does is vibrate back and forth.